Okay, let's see where we stopped. So last time I made one mistake. I want to make sure I fix that. The supernova that happened in 1987. Okay, it was all over the news. It was a type 2 supernova, not type 1A, type 2. So it was a massive star collapsing, rebounds, like there was a rebound, and it went as a supernova type 2. And at the time, we had the technology to really uh, report on that event, right? To follow what happened next. So you can Google it. Okay, it happened in the Large Magellanic Cloud. So when you have a massive star, okay, everything will be cooked, starting hydrogen to helium when it's on the main sequence. Then it's going to leave the main sequence. It's going to be a super red giant. Maybe it will become a super blue giant, and then the super red giant. You can oscillate between both red giant and blue giant, and it will cook everything here up to iron. Iron is a death sentence. When the star starts to fuse iron, it can't. Okay, because iron is very stable. That's when it will collapse. Okay, and then rebound, and you have a supernova type 2. Okay, now during that collapse, here everything will be squeezed so much. So remember, for the final, what will hold a white dwarf or a brown dwarf? It's called electron degeneracy. So when you try to squeeze electrons, they get very agitated, they hate each other, they cannot stand each other, and they push each other out. So that will provide enough pressure to balance gravity out, right? But here, the core is going to collapse. It's going to go over 1.4 times the mass of the sun. So electron degeneracy cannot balance out gravity. They will combine with protons, so electrons and protons will fuse together, if you want, and it will give you neutrons. Okay, so that's why it's called a neutron star. Now, if you go even over a limit, which is called the Oppenheimer limit, which is almost like between 2 and 3 times the mass of the sun, even neutron degeneracy cannot balance out gravity. Everything collapses, and then you have a black hole. Okay. I have a video that I forgot to show you. Massive star collapse somewhere. Star collapse. Do you see something called massive star collapse? MMM. Cannot find it. Well, I have this one, which is nice.
And I have an animation of what happens once we do that. So in this animation, we're zooming into the center of a red supergiant, and you'll see the colors in the center of the star change to represent different fusion processes that are occurring. As we switch from fusing hydrogen to fusing helium, as we switch from fusing helium to fusing something like carbon, you'll see the color change again. And the star will progress through different fusion sources until it attempts to fuse iron. This goes terribly for it. And then in less than a second, that iron core implodes. All of the material in the outer layers of the star tumbles down onto that imploded core and then bounces back out. And that rebound bounce gives us this unbelievable explosion that we see as a core collapse supernova. Disrupted. And I haven't.
So it's supernova type 2. Okay. Then I have this video here, so I might get in trouble because they don't like me to put videos from this website. So I might have to remove it from YouTube.
Quantify the transition.
But she's going to talk about the mass limit, right? So if you go over 1.4 times the mass of the sun, you're going to get a neutron star. And then if you go over another limit, then you get a black hole.
White dwarf to neutron star to black hole. Suppose we have a dead star and an imaginary dial that lets us change its mass. We'll set the dial to one solar mass, the mass of our sun. This produces a white dwarf, a spinning sphere of white hot matter about the size of the Earth. As we increase the mass by turning the dial, gravity gets stronger, the white dwarf gets smaller, and it spins more quickly. Once we turn the dial to 1.3.
So at that point, you have electron degeneracy. Okay, because there is no more fusion in a white dwarf. Okay, it's already dead. So gravity is pulling toward the center, and then you have electron degeneracy pushing out. It's like radiation. Then you go over 1.4 the mass of the sun, either because it's in binary system with a red dwarf, or because it's just collapsing, a massive star collapsing.
9 solar masses. Gravity is strong enough to combine electrons and protons to make neutrons and neutrinos. This value on the dial is called the Chandrasekhar limit. The dead star is now a neutron star. It shrinks down to a sphere with a radius of about 10 kilometers, and the spinning can be as fast as hundreds of times per second. If we move the dial further, gravity eventually becomes strong enough to break down the neutrons, and the neutron star collapses into a black hole. This point on the dial is called the Tolman-Oppenheimer-Volkoff limit, and while its exact value is not known, it ranges from 1.5 to 3 solar masses. If you were to look at the ingredients of a neutron star, it wouldn't be 100% neutrons. The number one ingredient is definitely neutrons, but there are still some protons and electrons in there too. Because a rapidly spinning neutron star contains these charged particles, there will be a massive magnetic field. Just like on Earth, the magnetic field doesn't have to line up with the axis of rotation. Like a stellar lighthouse, the magnetic field sweeps across the sky, emitting regular bursts of electromagnetic radiation. Because of this pulsing signal, neutron stars are sometimes called pulsars. Neutron stars, like the neutron, were predicted to exist before they were observed. Almost as soon as a neutron was detected, astronomers Walter Baade and Fritz Zwicky predicted that a supernova could produce neutron stars. And in 1967, a pulsating neutron star was first observed. In the decades since, many more have been discovered.
Okay, it's a nice summary. Then we watched the one about, so that's a pulsar, right? So it's a neutron star, but it will behave like a lighthouse. So it's going to send beam, okay, beam of radio waves that we can detect on Earth. When the beam aim at us, okay, it's going to be beep, 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 and you can detect that with a radio telescope. And the first time it was detected, it happened in 1967. So I will talk about that. Okay, so we did that. So maybe maybe this one, neutron star, that will be a pulsar, right? See, it's like a lighthouse. You have those beams here. You have X-rays as well, radio waves, and it's gonna spin really, really fast. Okay, so we'll get back to the videos. Okay, so 1987 A was a type 2 in a large Magellanic Cloud, which is one galaxy that orbits our own Milky Way. Okay, Betelgeuse is a good candidate, which is a supergiant, but it's a massive star, so it should go to supernova, but we don't know when it's going to happen. Here you have other examples, neutron star. So interestingly, I don't know if you remember this guy, Fritz Zwicky, a genius. He was working for Caltech, but his colleagues, everything is connection, connection, connection. That's why all the people you meet in this class, you have to make those connections. You never know. So anyway, his colleague, didn't want to take him too seriously because he knew that he was super intelligent, right? He was a genius. He was like Newton, but he will go around talking about his colleagues, saying they are spherical bastards. Why spherical? Because it doesn't matter which way you look at them, they are bastard all the way around. So if you want to make friends, that's not the way to make connections. But anyway, he was a genius. He predicted dark matter. He didn't predicted it. He detected it. And then he showed that dark matter should exist. And then he also predicted neutron stars. He predicted that when a massive star collapses, okay, what will be left behind, the corpse, okay, will be neutron star. But it was not detected at the time yet. He did detected supernovae, but he didn't detect neutron star yet because there is no radio telescope that could detect them at the time. So the detection happened, very famous story, with Jocelyn Bell, okay, 1967. So she was British. I mean, she is British. I think she's still alive. And now she has been knighted. So, for example, Isaac Newton, okay, he was knighted. So he became Sir Isaac Newton. So she was knighted by the Queen. So she's Dame. Dame is for a woman, right? So Dame Jocelyn Bell. So anyway, when she was a graduate student, her advisor built a radio telescope, and for the first time they detected a pulsar. But at the time, they didn't know it was a pulsar. It was like beep, 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 beep. So they call it Little Green Man. So could be a question on the final, okay? Little Green Man, because they thought it was like extraterrestrial life trying to send signals in the universe. So Little Green Man, that's the term they used. And then so they were about to publish the paper, and then all of a sudden they detect another beep 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 beep. So it could not be it, right? So they understood that they had made this huge discovery of the first pulsar. Now, the sad story was that her advisor didn't share the Nobel Prize. So, her advisor, okay, he's the one who conceived that radio telescope, but she is the one who detected it and then published her paper or thesis, saying that was a pulsar. But he didn't share the Nobel Prize, and many scientists in the community think that it's really unfair that she was ripped of that. But she apparently she's a nice lady, so she took it okay. So anyway, that was in 1967. Okay, so big breakthrough. So here you have a neutron star. It's gonna pulsar. It's gonna spin really, really fast and send a beam of radio waves. So if I ask you, no, for the final, how did they call it? They called that the little green man. Little green man because they thought, oh, it's like some extraterrestrial life, right? So that's what, boom, do you see the beam? Boom, right? Okay, let's see if I have that. You can have mergers of neutron stars. Okay, I think we watched that.
IUG outburst seen in April 2020.
I think we did that, right? Uh, you can have two neutron stars orbiting each other, and then they get closer to each other, so they're gonna lose energy. They're gonna make gravitational waves, and they can merge to form a black hole. So it's a very violent event. And this is a simulation, but it's based on real data. So that was before AI. So this is all computer simulation, but what is left behind is a black hole. I don't know what is that. You have two neutron stars. So two neutron stars can merge together and it can give you another neutron star. So here it's a pulsar and it's a magnetar. They call that magnetar because of the very, very strong magnetic field. I don't know if I should.
Teaspoon boys would weigh about 4 billion tons. Astronomers have just discovered a pretty young pulsar, which seems to be the most powerful one ever observed. Pulsars are basically neutron stars that emit beams of electromagnetic radiation and they point straight toward Earth. Neutron stars are some of the densest objects in the universe. They come after massive stars explode, so they're practically the collapsed cores of massive stars. Although these objects boast about 1.5 times the mass of our sun, they typically measure about 20 kilometers across. A teaspoon of these bad boys would weigh about 4 billion tons. I know, mind blowing. We have a good understanding of how they form, but we have a lot to learn about their evolution. The newfound pulsar star is known as VT 1137-033. Astronomers and these names, but I don't blame them. There are just so many stars out there that you have to design codes for them so that they can keep track of them more easily. So the new pulsar seems to be extremely energetic. Scientists say it appears it's about 10,000 times more energetic than the Crab pulsar. And more surprising is that it has an even stronger magnetic field. It's so strong that no one is sure whether it belongs to another class of neutron stars, magnetars. Magnetars have the strongest magnetic fields in the universe. Their magnetic fields typically range from 1,000 trillion times stronger than Earth's to somewhere between 100 to 1,000 times stronger than a pulsar's. If the newfound pulsar is instead a magnetar, this would mark the first time astronomers have caught a magnetar in the act of appearing. Astronomers found the new pulsar using data from the Very Large Array Sky Survey, a 7-year project of the National Radio Astronomy Observatory, which is conducting 3 full sky scans from the Very Large Array, ELA, near Socorro, New Mexico. When finished, it will have mapped about 80% of the sky over the course of 3 separate runs. Scientists first observed the pulsar in 2018. It lies in a dwarf galaxy about 400 million light years away. Because we observed this object again in 2019, 2020, and 2022, it's obvious that it isn't just a transient radio burst of some kind. Right now, the object appears to be a pulsar wind nebula, a neutron star that accelerates nearby charged particles at almost the speed of light. Wonder how it does that? Well, as the pulsar spins extremely fast, hundreds of times per second, its magnetic field and radiation beams sweep through the surrounding nebula, causing gas there to ionize and emit radio light. Another interesting thing is that the pulsar appears to be in its infancy, between 14 and 80 years old. Astronomers came to this conclusion because the pulsar wasn't seen in an earlier BLA sky survey made in 1998. This suggests that the object is one of the youngest neutron stars yet found. The finding was announced on June 15th at the 240th meeting of the American Astronomical Society in Pasadena, California. You can find the source link below. If you like this video, please consider subscribing and click the
Okay, it's a cool video. You find it on the YouTube. And then let's see if I have one more. So we did this one, type 1A. I think we did this one. And then there was one more somewhere about okay, so remember you can have a nova. Okay, when you have a, let's go back because I forgot to show you this video. So when you have a white dwarf and a red giant, okay, and if it gets too close to each other, the material from the red giant can start to pile up on the white dwarf, and you can have a superficial thermonuclear reaction, but it will not destroy the white dwarf. And I'm running out of battery. So this is the case here. So in that case, it's called the nova. So it's just superficial. And it's just a video about that. So that happened in 2021. And every 15 years, right, you're going to have this thermonuclear reaction. Every 15 years, it piles up, piles up. Boom. You have a thermonuclear reaction. So piling up, brightening, brightening, gravitational energy. Mm. Aïe, 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 there's a high frequency noise somewhere. So the white dwarf here and the red giant. Okay. So it happened in 2021. So, okay, for those who just came, again, on Wednesday, we might finish today. I might talk about the final today or I might not. Let's see how it goes. But if you come Wednesday after I'm done, I'll give you extra credit for showing up. Now, I cannot extend anything past Wednesday. Okay, I cannot reopen anything past Wednesday because I have 300 students all together. I'm not reading my emails. Okay, so make sure if you need anything, ask me today or ask me Wednesday. You can spread the word on the WhatsApp group if there is a WhatsApp group. I think there is a WhatsApp group. Okay, so neutron star again, just to give you an idea of the size, that will be the sun, then that will be Jupiter. You see, you can put 10 Jupiters across the sun, and then you can put 10 Earth across Jupiter. That will be the Earth and the Moon. Moon is quite large, that's why it's called a double planet system. And then you have the Moon here relative to 100 radius circle, and then relative to this, that will be the neutron star. So that will be about that size here. This is Chicago. So it's really, 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 really squeezed because gravity almost won the game. And then you have neutron degeneracy holding, pushing away gravity. And if it's not large enough, then you're gonna have a black hole. And then you have very okay, so that's we talked about that previously. The first exoplanets ever found were found around a pulsar, which was very weird. So that was in 1993. It was weird because the pulsar, it's the leftover after a supernova, and if the supernova happened, the planets could not have survived. So it must be that those planets, they were looking for a home and got attracted by the pulsar, captured by the pulsar. Okay, so that was the first exoplanets. And then you have very interesting special relativity effect with a pulsar because gravity is so strong. Okay, when radiation is trying to escape from the neutron star because gravity is so strong, it's going to lose energy. But a photon, okay, light, cannot go slower. If something loses energy, like you push something outside, it's going to move, it's losing energy, it's going to slow down. But you cannot slow down light. It cannot go slower. It has to go at the speed of light. So it's going to lose energy in the form of radiation. So let's say it goes blue to begin with, or in UV, it's going to be redshifted when it's trying to escape. Okay, because the neutron star, it's going to have the space-time, right? So radiation, when it's going to try to escape the wrapping of space-time, it's going to lose, it's going to be red shifted. So a lot of opportunity to study special relativity. It's like something is trying to go up here, it's going to lose energy. And of course, the ultimate fate will be a black hole. When neutron degeneracy is not enough to fight against gravity, so what's going to happen? You go over mass limit, which is called the Oppenheimer. You remember Oppenheimer from the movie, right? So Oppenheimer, he was part of the Manhattan Project. But anyway, that's not the only thing he did. So the mass limit, okay, is between 1.5, like no, between 2 and 3 times the mass of the sun. Then it will become a black hole. Okay, and then you have something here called the event horizon. If light crosses that line here, the event horizon, it cannot escape. That's why a black hole is black. Okay, and the first black hole ever detected is called Cygnus X1. Okay, and there was a whole story about it, but you had like a massive blue star in a binary system with a black hole. And at the time, they didn't know it was a black hole. And then they did study on it, and they found out it was a black hole. So as the material goes inside here, you're going to have bursts of X-rays. So that's why it's called the X-ray binary system. Okay, you can Google the story. Okay, Cygnus X1. X is for X-ray. First black hole detected when 1964. Okay, for first they were not sure it was a black hole, and then they got data to confirm it was one. 1970s. Okay, so the first black hole detected. So there is a whole story, very famous story about Stephen Hawking, because he had a very famous bet with another astronomer, and Stephen Hawking said it's not a black hole, and he lost the bet. And then he wrote a special paper saying, "I lost the bet." So it's a very famous story. Let's see. So they had a bet with that physicist here, and then Hawking. It took him a long time, 1990. Okay, he considered that he was wrong. Oh, and they bet on the subscription to Penthouse magazine. That's funny. Okay, so it's a very famous story. If you're interested, you can look into it. Black hole. Okay, I have a very nice video.
Black holes are among the most fascinating objects in our universe, and also the most mysterious. A black hole is a region in space where the force of gravity is so strong, not even light, the fastest known entity in our universe, can escape. The boundary of a black hole is called the event horizon, a point of no return, beyond which we truly cannot see. When something crosses the event horizon, it collapses into the black hole's singularity, an infinitely small, infinitely dense point where space, time, and the laws of physics no longer apply. Scientists have theorized several different types of black holes, with stellar and supermassive black holes being the most common. Stellar black holes form when massive stars die and collapse. They're roughly 10 to 20 times the mass of our sun, scattered throughout the universe. There could be millions of these stellar black holes in the Milky Way alone. Supermassive black holes are giants by comparison, measuring millions, even billions of times more massive than our sun. Scientists can only guess how they form, but we do know they exist at the center of just about every large galaxy, including our own. Sagittarius A, the supermassive black hole at the center of the Milky Way, has a mass of roughly 4 million suns and has a diameter about the distance between the Earth and our sun. Because black holes are invisible, the only way for scientists to detect and study them is to observe their effect on nearby matter. This includes accretion disks, a disk of particles that form when gases and dust fall toward a black hole, and quasars, jets of particles that blast out of supermassive black holes. Black holes remained largely unknown until the 20th century. In 1916, using Einstein's general theory of relativity, a German physicist named Karl Schwarzschild calculated that any mass could become a black hole if it were compressed tightly enough. But it wasn't until 1971 when theory became reality. Astronomers studying the constellation Cygnus discovered the first black hole. An untold number of black holes are scattered throughout the universe, constantly warping space and time, altering entire galaxies, and endlessly inspiring both scientists and our collective imagination.
So I think this is a great video. It's very nice, summarizes everything. Now you have supermassive black holes at the center of every galaxy, like our own. I just have to find the right video. Supermassive black hole.
A black hole is a region of space where the force of gravity is so strong that nothing, not even light, can escape. Anything with mass can become a black hole. Say you weigh 150 pounds, and I compress you down to a size smaller than a quarter, then you would become a black hole. Or take the sun, compress the sun down to a radius of 2 miles, and the sun collapses and becomes a black. One way to make a black hole is through the death of a star. Do you have a star that is 20 times the mass of the sun or more? Then as that star evolves through its life, it's going to explode as a supernova. And then what's left after the explosion is a black hole. But then there are black holes that are much, much bigger, so 1 million to 1 billion times the mass of the sun. And those are called supermassive black holes. Not just massive, that's not good enough. It's gotta be supermassive. And turns out that every big galaxy has a supermassive black hole at the center. What my group does is we ask the question, how do these supermassive black holes build up their mass? We don't understand that part. One of the great mysteries here is, where do these objects come from? If we're observing these supermassive black holes everywhere, how do they achieve these huge masses? These supermassive black holes, they don't suck in material. That's a very common misconception. If you see a black hole, you're not just going to be sucked straight into it. You are going to orbit around it just like it's a point mass. So for example, if our sun were to become a black hole, we would keep going around it. What I first thought about was, why can't you just have some galaxy that just has a ton of gas in it and just feed this black hole to make it into this billion solar mass black hole? But those kinds of processes of just directly feeding it, that's not enough material to make it grow to what we observe. So we specifically as a group study supermassive black holes that are often undergoing some sort of large merger between galaxies. And we think that maybe supermassive black holes merging together is one of the contributing factors that could explain why they're so big in the current universe. So we look for what we call a pair of quasars. So a quasar is a supermassive black hole with this big accretion disk of swirling gas and is really, really bright. So a quasar is like a black hole that you can see. The biggest paradox about black holes is that they're the blackest things in the universe, but they're also some of the brightest things in the universe. And that's because when you have a black hole and some gas is being gravitationally pulled towards it, the gas doesn't just fall straight in. Just like if you fill up your bathtub with water and you pull the plug, the water doesn't just fall straight down the drain. It kind of swirls around and then goes in. So the same thing happens with gas around a black hole. Gas is pulled in gravitationally, it swirls around and forms this thing called an accretion disk. It's just a disk of gas kind of waiting its turn to fall into the black hole. But the black hole is so much mass, you're so close to it, that gas is swirling really fast, it gets heated up and emits lots and lots of light. So that accretion disk can create more light than all the stars in the galaxy combined. Say you have two galaxies, each with its own supermassive black hole at the center. When these two galaxies merge together, the two supermassive black holes come together to form a black hole pair. The black hole pair then merges together to become one more massive black hole. The galaxy merger itself also creates a huge disturbance of the stars and gas in the emerging galaxies. It's like a train wreck of disturbed gas, with a lot of the gas being funneled towards the center of the galaxy and feeding the supermassive black hole in the center. What we're trying to do is learn about how much galaxy mergers can change the way that black holes and galaxies evolve together. It is fascinating to imagine that something the size of a penny, that would be a supermassive black hole, could have an impact on something as big as the Earth, that would be the galaxy. The way that black holes evolve is tightly connected to the way that galaxies evolve. If I was plotting the mass of the galaxy against the mass of the black hole, you would find that this is a tight line, with the mass of the black hole increasing in step with the mass of the galaxy. So to understand how galaxies evolve, you got to understand how black holes evolve. I think we're unique as a species because we pay to build telescopes to understand these big questions of our origins and where we came from. Do you think a monkey would give up one banana to understand more about where it came from? No. A monkey would hold on to that banana and say, you can't take it away from me. So you're not going to be able to go out and change anything about the way the universe is evolving and, galaxies colliding. They're not going to impact you on a personal level, but our lives would change if we could think even on a little bit bigger context, like a global context and taking care of our planet, for example. This is just part of pushing ourselves to look a bit bigger than just what's right in front of our noses.
It's also a very nice video. And then when you have a black hole after a supernova, you're going to have gamma rays burst. So I don't know if I have a video about that. Black hole supernova gamma rays burst. I cannot find it, but this is a video that it's very, I cannot find it in English. Okay, so it's not English, but I can find it in English, but I cannot find this part. So it's an episode of The Simpsons. It's a very famous one where he's trapped in the black hole, and what happened to him, it's something that is described as spaghettization. Like if a human will go close to a black hole, cross the event horizon, right? So it's the point of no return, he will be spaghettized if it's a small black hole. Why? Because you have a lot of differential, so a lot of difference in the pull from gravity, right? So gravity will pull harder on your feet, that's it's pulling on your head. The differential will be big. We don't feel that here because gravitational from the earth is not that strong. Although if you look at older people, like very old people, you see that gravity at the end, okay, is winning the game as you go. You collapse. But in that case, this is called spaghettization. So that's going to happen to Homer as he goes through the black hole. So it's a very famous episode, and I thought it was funny. So it's not in English, but you can, watch the cartoon. You understand?
Pienso que estoy derrochando una fortuna solo por estar aquí. Bueno, hay que aprovecharlo. Vaya con el fuego.
So that's the
Pues,
you got it right. It's a fabric of space time.
si es persona. ¿No has visto bien la película? Todo lo que desconozco de la astrofísica, ojalá hubiera leído el libro de aquel tipo de la silla de ruedas. ¡Ah! 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 Absorbido por un agujero negro, desapareceré en el olvido, seré nada que se me vendiera al otro lado de la noche. ¡Yo te salvaré! Se está chupado.
So, so the point is that we don't know what's beyond the black hole. Okay, a black hole can be a wormhole connecting to another black hole, and then the time stops, right? The relative to someone looking at you from outside, the time stopped. Okay, it gets slower, runs slower, 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 and then it stops. And then we don't know what's inside the black hole. It's a big mystery. So some people think it's another universe, right? So you go from the Simpson universe to our universe. Who knows? So it's a very funny, interesting cartoon. And sorry, it's not in English. I tried to find it. I could not find it in English. And then when you have two black holes merging together or two neutron stars, you're going to make what is called gravitational waves. But we already talked about that.
Visible light from the first stargazers, ultraviolet and infrared light,
You done?
space telescope,
You are done. That's it. You're tired.
microwave and radio
You are tired.
blasting from the cores of galaxies.
Or you're listening to something else. You're listening to something else.
But there are other vibrators. The collision unleashed the energy of a billion trillion suns in a fraction of a second. That energy is still spreading outward in the form of gravitational waves,
So
space-time
it's a
distortion
merger of two
rippling
black
across the
holes.
universe at the speed of light. As a gravitational wave travels, it compresses space in one direction and stretches space in the other, like sound going sideways. This push and pull weakens with distance. The wave fades to a whisper, so faint that physicists long thought that gravitational waves would never be measured on Earth. But in Louisiana and Washington, two of the most sensitive detectors ever built have been waiting and listening. Astronomy has drawn ears. This is LIGO, the Laser Interferometer Gravitational Wave Observatory. Each detector has an L-shaped antenna, arms 2.5 miles long. Inside the ends of each arm, mirrors of ultra-pure glass are isolated from the noise, heat, and vibrations of the outside world. A beam of laser light measures the separation of the mirrors. The beam is split and sent toward mirrors at the end of each arm. If the arms are precisely the same length, the returning beams cancel each other out, and LIGO's detector sees no light. But a passing gravitational wave would stretch one arm and squeeze the other. The resulting discrepancy is tiny, a fraction of the width of a proton, but enough to misalign the beams and light up the detector in a rhythmic pattern. On the 14th of September 2015, LIGO detected a flickering light and turned it into a sound wave, a chirp. It was the echo of the marriage of those two black holes, a cosmic cataclysm that happened a billion years ago. Hearing a gravitational wave has opened up a new kind of astronomy. For the first time, we have ears as well as eyes on the heavens. And LIGO is only the beginning. In January of 2016, the LISA Pathfinder spacecraft arrived at its destination, a spot in space 1 million miles from here, where the gravity of Earth and Sun cancel each other out. A quiet place to attempt the impossible, keeping two cubes of gold and platinum in perfect freefall and perfectly still. The mission is a test, groundwork for a future mission, ELISA. 3 spacecraft 1 million kilometers apart, linked with lasers, lying in wait for gravitational waves. The largest instrument ever built would be dedicated to Einstein's elusive waves. From nearby black holes to the first rumblings of the Big Bang itself. From ultimate birth to ultimate doom. Ears tuned to the invisible music of the cosmos.
Okay. So this one was very nice. I'm sorry if it's annoying class for some of you, obviously. Okay, so what I'm going to do, I'm going to open the pop quiz now, and we'll talk about the final on Wednesday. And remember for the extra credit, but we are done, okay? All the material for the final I already covered, and maybe on Wednesday I will show you just one video about measuring the size of the Earth, which I think is really cool. Okay, so I'm going to open it for you.